Stephanopoulos, and I am joined by Enes Barada, Ariana Kresniak, Diego Mateos, Nikit Bandit, and Rhonda Kashola. We are Team B, and we have designed a rocket flight stabilization system for the York University student rocketry team, Arbalest Suborbitals. Arbalest is entered into the Beginner Launch Challenge of Canada's first university rocketry competition, Launch Canada, in which the team has designed a hybrid rocket, Goose 1, with a goal of reaching an altitude of exactly 10,000 feet. The vehicle will also be carrying a camera payload, so for this goal, our team was charged with designing a unit that can control the vehicle's roll, pitch, and yaw. Reducing roll will result in better camera footage, and controlling pitch and yaw will result in a higher peak altitude. Our design is a unit that employs 4 radially symmetrical canards, each controlled by a digital servo. These servos, along with the controlling electronics, are mounted onto threaded rods using 3D printed parts, and the whole unit is housed within a composite body tube. I'll now begin with a quick video demonstration of how the unit operates. To begin with, there are 4 screw switches that turn on the unit. The bottom switch turns on power to the microprocessor, the TNC 4.0. The second switch turns on power to the control altimeter located at the bottom of the unit. The third switch turns on power to the servos, and the top switch turns the unit into its overridden mode, or its display mode, where it shows how it will behave in flight. We'll begin by turning on power to the TNC 4.0. You can see that it's getting power when a red light is visible through this hole here. After which, I'll turn on power to the servos. The servos will be getting power properly when they are fully aligned. Now the unit needs to be calibrated before it can be installed into the vehicle. We'll begin this by calibrating the accelerometer. For this, it needs to stand in 45 increments on its major axis. Next, the gyroscope needs to be calibrated. For this, it simply gets moved around in a figure 8 pattern. And then, it needs to be calibrated with the magnetometer, which needs it to sit still for a moment. Once fully calibrated, the servos rotate through their full rotational angle 3 times. This indicates that the calibration is complete, and it also checks that the servos are operating properly. Now, the unit is ready for installation. Before installing into the vehicle, we'll also have to make sure that the altimeter, the Raven, is on. To do this, we'll screw in the second screw switch, and you'll hear that it's on when it beeps out the tones of its altitude parameters. Let's now turn on that override switch and see how it operates in flight. It'll first begin by going into what's called drag mode. Essentially, what it's doing here is rotating 2 of the canards clockwise and 2 of them counterclockwise, and in doing so, increases the net cross-sectional area of the unit without inducing any roll. This results in more drag for the vehicle, and it's used in the late stages of the flight to hone in the final altitude the vehicle will reach. Now, turning the servos back on, we can see it enter the rest of its display mode. Every 10 seconds, it does drag mode, just so that you can see what it looks like. Now that the unit's powered on, we'll take a quick look at pitch and roll control individually to see how they operate. You can see that when I pitch the vehicle over, the canard tries to stay vertical, no matter what orientation the unit is in. This is also done on any direction, and the canards will all move together in order to accomplish this. Setting it still, but just rotating it, you can see the roll control in action. The faster I rotate it, the harder these canards are going to move to counteract that. You can also see the allocation of roll and pitch control that ensures that none of the servos max out their angles. If I tilt the unit over and then rotate it, you can see that these canards, the ones handling the pitch, don't move much. However, the canards on the other axis move a lot, as they are now doing all of the roll control. There's also one major safety aspect that's hard programmed into the unit, which is that when it tilts beyond certain angles, in this case 30 degrees, the unit locks into its passive mode where the canards stay aligned with the vertical. This was one of the competition regulations set by Launch Canada. You can see it when I rotate the unit beyond 30 degrees. the canards all go vertical no matter what the unit is experiencing. But when I rotate back, it is now available for control.
Our servo mounts have been 3D printed to encourage easy manufacturing and rapid prototyping for design iteration. They are made from PETG due to its high resistance to water and UV light, good strength at higher temperatures, and low thermal expansion for accurate tolerance. The mounts have been designed with venting channels to prevent the servos from overheating. Friction fits have been incorporated to attach the two mounts, firmly hold the servos in, mitigate their vibration, and allow the rotation of the canard axle mount with adequate clearance. The actuators we chose are low-profile metal-geared digital servos. They offer high torque and rotation speed while fitting our desired layout. They have an acceptable resolution and are easy to command using a pulse width modulated signal. These servos operate on a voltage range between 4.8 to 6 volts.
So the servos are powered by two 3.7 lithium polymorph or LiPo batteries, which are wired in series. So we actually used a voltage regulator to bring down these two series LiPo batteries to the operating range of the digital servos. The electronics are soldered onto an R4 board, and the rest of the electronics package we have in the unit is a barometric pressure sensor, an inertial measurement unit, IMU, an altimeter, and a microcontroller. All of these sensors directly interface with our microcontroller. So the IMU we have today is the Adafruit BNO055. It actually has internal filtering and sensor fusion built in, so it fuses the gyroscope and the accelerometer to provide a low drift, low noise orientation information. While in this mode, it actually outputs unfiltered roll information, which is then used as a direct input for roll control. All of this information is given in an absolute frame, meaning it actually indicates vehicle position with respect to the surface of the Earth and magnetic field. And the barometric pressure sensor we have is also an Adafruit device. It's the GY63, and this unit provides the temperature and pressure information, which is then used to calculate the current vehicle altitude. This altitude is then inputted into the onboard altitude trajectory prediction system, which then can conditionally enact drag control of the unit. The altimeter we have selected is the Featherweight Raven 4. The target altitudes have been programmed onto the altimeter to detect the changes of flight of the unit. So it can detect launch and tell when the unit will enter the boost phase. It can tell when the boost phase has ended and the coast phase has begun. And the signals from this altimeter are then sent and wired to the microcontroller to actually conditionally execute control code logic programmed for the different stages of flight. Similar to the servos, all of the electronics are mounted on a 3D printed PETG mount. So now let's look at the housing and bulkheads. So you can see on the fuselage tube, we have a series of holes all through it. So these three set of 4 holes allow for air to circulate through the unit to cool the electronics and actually enable the barometric pressure sensor to actually sample pressure and temperature of the outside environment. This hole allows the TNC to be connected to a computer using a micro USB to allow for software changes without needing to disassemble the unit.
There are high-density fiberboard bulkheads at either end of the unit that serve to enclose the unit and offer rigidity to the fuselage. Mounted to the middle of the top of the bulkhead, there is an eye bolt that the parachute cables are connected to. Threaded rods transfer tension loads through the unit to the propulsion section below and avoid impartial loads onto the 3D printed mounts. The bottom of these rods is directly mounted into the top of the propellant tank. The eye bolt and aluminum reinforcement are estimated to experience a worst case of 1600 newtons as the main parachute is released. We got this estimate by writing a MATLAB script that simulated the unfurling of the main parachute in different time frames. If the parachute were believed to unfurl instantly, then the force experienced would be approximately 5500 newtons. But the team believes that this would be an unrealistic worst case. By considering the parachute release is being distributed over as little as 0.25 seconds, the force is shown to be more reasonable. To validate the bulkhead reinforcement beam, the team performed a finite element analysis to simulate the beam's reaction to the forces.
Like the servo mounts, the canard axles are 3D printed from PETG. The flight axles will be overwrapped with carbon fiber or made from metal to increase strength. Our canards are handmade from 24-gauge stainless steel sheet metal. They are a swept, clipped design, as they are designed for a subsonic to transonic vehicle velocity. Similar to jet plane wings, these canards are swept backwards as to decrease their drag and increase their strength at higher wind speeds, and their edges have been clipped to reduce drag from wingtip vortices. The canards operate as small wings, located at the front of the vehicle. They are placed here so that the small lift forces they generate can have a larger impact on the angle of the vehicle. The canards were made with sharpened edges to decrease their drag, and by changing the angle of the canards relative to the oncoming air, which is also known as the angle of attack, lift is generated. The unique lift forces from each canard can then be combined to affect the roll or the pitch of the overall vehicle. The design of these canards was scaled off of pre-existing canard designs from wind tunnel test papers found on the NASA Technical Report Server. This scale design was then validated using computational fluid dynamics and the open source rocket simulation software, OpenRocket. As the rocket flies, the faster it moves, the more air will be passing over the canards and they'll start to vibrate. These vibrations can destroy the canards if they are not designed to be stiff enough to handle it. There is a critical speed for any canard design called the flutter velocity, and it's the maximum speed a canard can operate at before it's at risk of being destroyed. This calculation was performed on our canard design, and they were found to have a safety factor of 5.9, which is significantly higher than necessary.
The angles from the canards required to control roll are determined using derivative gain equation and data from the gyroscope. This means that the faster the vehicle rolls, the greater the angle the canards will be moved to counteract this roll. To control pitch, the canards are moved in such a way that they remain pointed in the vertical direction regardless of the orientation of the unit. This is done using IMU data and calculations in Euler numbers. To determine when to increase the drag of the vehicle, the final altitude was predicted using a 3-degree of freedom trajectory model based on the discretized Feskin-Zmailovsky rocket equations. The accuracy of this model was validated with results from the rocket flight simulators, OpenRocket and RAS-Aero. The roll, pitch, and drag angles are prioritized in that order because the surface cannot move fast enough to control pitch at high roll rates, and the altitude prediction equations lose accuracy when the pitch angle is high. The canards will enter the drag mode if the peak altitude is over-predicted. This only occurs if pitch and roll stability are within a respectable range.
All the aerodynamic forces are applied at the center of pressure, and the vehicle will experience this as a rotation about its center of gravity. As the vehicle experiences an external torque such as a gust of wind, the vehicle will be angled slightly off its flight direction. This angle is known as the angle of attack. The lift and drag forces applied at the center of pressure will push against this disturbance, acting as a restoring force to correct the flight path and maintain passive flight stability. This only occurs if the center of pressure is below the center of gravity. Standard Barrowman equations are employed and validated with OpenRocket as a function of the vehicle velocity and angle of attack to estimate the center of pressure and how it will change as we rotate our canards and change the angle of attack. To maintain a stability margin of 1.5 calibers, canard angle thresholds of 5 degrees, effectively a 10-degree cone, are incorporated into the control code to ensure compliance with Launch Canada requirements for flight stability in all possible control system configurations.
We are Team B, and this has been a review of our aerodynamic control system. We greatly appreciated working on this project, as it exposed our team to hands-on work. We were able to produce a manufactured unit despite the restrictions and challenges presented by COVID-19, and we were able to diversify our skills by engaging the software, electronics, and mechanical systems from both a theoretical and manufacturing perspective. We got our hands on not just simulations, but tools as well, and worked together to engage rocketry, because in this case, it literally was rocket science. And our team was able to engage the greater rocket community by being connected with Launch Canada. So we truly appreciate being able to have done this project.